Thank you very much, Georg. And so what is this talk about? So Georg asked me to briefly present OpenMP 5, or I think he asked for something like the latest editions of OpenMP. And I said, at least for me, it's impossible to really do that briefly. So we decided to have two contributions to the seminar series for the next few weeks. And this one will cover tasking in OpenMP, because I personally like tasking a lot, and I still believe it's underrepresented in HPC applications with respect to what that feature can actually provide for the programmer. And I have to admit, I lied to you. So this is about tasking in OpenMP version 5.0 and 5.1. So what is OpenMP? And Georg said OpenMP is around for quite a while, but at the tutorials, many people I met still believe OpenMP is pretty much about parallel region and the work sharing. And if you take a closer look at the standard or books and also our tutorials, you will notice that OpenMP has been extended in recent years. So it still aims to be the de facto standard for shared memory parallel programming, targeting C, C++, and Fortran. And it still builds on compiler directive, runtime routines, and environment variables. So this didn't change, and only with respect to C++, in future versions, the aspect of compiler directives might change. But all those features that have been added over the years made look OpenMP really different. And depending on where you come from, OpenMP might look completely different. And that's always interesting when I talk to a group of people where some have been using OpenMP for almost 20 years, while others are rather new to OpenMP. And for this latter group, often tasking comes as a first choice for almost every problem. That's not necessarily right, but this is to some extent also what this talk will be about. And I like this elephant picture that my colleague Ruud van der Paas came up with. And what I'm trying to say here is that OpenMP tries to incorporate many different aspects of parallel programming for modern architectures into a single standard. And we still have the parallel region and the work sharing, but this has been complemented with support for SIMD or vectorization, whatever you might want to call it. We have tasking, which this talk will be about, for irregular programming, for example, or irregular code structures. We have accelerators, that means support for GPUs, FPGAs, and so forth. We have memory management that supports the programmer in dealing with different kinds of memories, and so forth. Of course, that makes OpenMP as a whole complex, but I still believe that you can increase this complexity incrementally. That means you only have to use those features that are important for you with respect to performance or functionality of your code. And I believe it's also a unique selling point to have all this implemented in the same standard, because this enables compatibility. Yeah? If you want to use work sharing and tasking, and then a compiler-specific extension to support vectorization, that in many cases you as a programmer will run into a problem. And this is, from my personal opinion, the main motivation for incorporating all aspects, like shown here, into OpenMP. Good. By the way, this is touching on, I hope, all the interesting aspects of tasking. At IC, we have a half-day tutorial on that, and at SC, this year we will probably, I think it was confirmed today, we will have a full-day tutorial on that with actually hands-on exercises. So I would be happy to see you there again if you want to get even more experience with OpenMP for yourself. So let me start this overview with a brief motivation. And, you know, for computer scientists, sometimes I get the impression that Sudoku might be one of the most important problems out there. And this is why I've selected that for my motivation. So I assume you all know the Sudoku challenge or the Sudoku problem. And what I try to sketch here on this slide is a very simple algorithm. So you start the algorithm with an empty field, like this one in here, and then a really stupid brute force algorithm tries out all the numbers. So it adds up, or it tries out all the possible numbers at the current empty field. And if a number is a candidate, that means there is currently conflict and the chance for solving the Sudoku board, it goes to the next field. And at the very end, the algorithm waits for the completion. So how can we parallelize that with traditional OpenMP? If you take a look, you can identify a for loop, like, for example, show here, try all the numbers. In this particular field, there might be a for loop from 1 to 16. But the algorithm is formulated in a, I try to hint at that, recursive way. So that wouldn't make it hard to actually use a parallel region in there, because if you use a parallel region in a recursive algorithm, you have to add some, let's say, logic to manage the total number of threads. After you have reached a few hundred of threads, the system gets under stress, and with 1,000 threads, I guess, on most boxes, your program will get killed. So we need something different. And actually, OpenMP tasking, and I hope you can still see the slides here. At least I have a Zoom window in front of it, can provide a solution like shown here. So first, we still need a parallel region. We need a pragma OMP parallel. And that parallel region gives us parallelism. Then we have a pragma OMP single. That might sound strange, but if you remember, that single gives us one thread that executes the body of this construct, and the others will jump around and wait at the end of a so-called implied barrier. So the idea is that we have a team of threads available for the parallel execution. But then here at this point, we have only a single thread that starts the execution of our algorithm, because we need one thread or task to start at the first empty field. And then we are going to use tasks. So that means at each empty field where we try out a set of possible, let me call them candidate numbers, we can put in this candidate number into a copy of the Sudoku board, and then from there continue on in parallel. So the idea is that all those tasks can run in parallel, executed by the team of threads that we have created with a parallel region, and therefore look at all possible solutions. And whenever there's a valid solution, it can print it, for example, to the command line or whatever this program is doing. At the very end, we need a task wait to be sure that all tasks have been completed. So far for the sketch. A few more details on all those constructs will follow in a few minutes. But I just wanted I want to be honest with you. This is a measurement with an older compiler on an almost ancient architecture, but the speed up numbers are not really impressive. So those bars that you see here is the parallel runtime, or the actual program runtime. That's what I wanted to say, of this program over the different numbers of threads. And the line you see is the corresponding speed up. And the speed up of something like 3.6 on, let's say, 32 logical cores is certainly not overly impressive. So while tasking gives us can give us great flexibility, for example, to parallelize such a recursive algorithm, as it is so often the case in life, we need some understanding of what's going on or what's happening in the background in order to be able to execute them later on. So during the course of this talk, I mentioned the solution to this problem, at least briefly, and I come back to that later on and illustrate that there can be better performance achieved. Let's start with the basics. I assume you have some basic knowledge of OpenMP, and I just wanted to illustrate the concepts of tasking in this sub-chapter. So what is a task? I tried to briefly explain that in the motivation, but now I would go back to OpenMP terms. So a task is a work unit. That means it's some code. This is the code you put into the curly braces, looking at the task construct in C and C++. And the data environment. This is a set of variables, for example, private variables that's part of the that are part of the task, or references to shared data. And finally, some internal control variables. These are internal settings of the OpenMP runtime to define the behavior of the OpenMP program. So tasks are code, data, and these ICVs. And whenever a task is encountered, it might be deferred. That means executed later on, or executed immediately. And in almost all cases, this decision is up to the runtime. And that's basically the idea. You express the opportunity of parallel execution of tasks, and the runtime is responsible to map this set of tasks to the available threads. And tasks are flexible because they can be nested. That was the case in my previous example using recursion. Tasks can create more tasks. Again, this is an illustration of nesting and so forth. And a task could actually include one worksharing construct, but then again, this worksharing construct is not allowed to have any further worksharing constructs nested inside it itself. The OpenMP language committee, when introducing tasks, decided that starting with version 3 in OpenMP, everything is a task. So that means even when a parallel region is being encountered, implicit tasks are created. But what we are talking about here are so-called explicit tasks. That means tasks are being expressed by the programmer. There's a special advantage of making everything a task in OpenMP, which only became obvious in OpenMP 4 many years later, because now with support for GPUs, which is a topic probably of the next talk, target constructs are also tasks. And having said that, it, I believe, becomes obvious how, for example, asynchronous communication, asynchronous kernel execution, and so forth with a device can be enabled, because a task in itself is a very asynchronous thing. So let's illustrate what's possible. With OpenMP worksharing, it's really hard to parallelize while loops. We can do so with a parallel construct and the single, and so forth. There are patterns to achieve that. And similarly, with recursive functions, we can limit the number of threads that are being created at individual parallel regions, and finally just executing with a single thread and so forth. But there is always some overhead involved of, I would call it, unnecessary synchronization because of semantics that come with those constructs, and tasks can provide a solution to that. So I try to illustrate it already. We have a concept of a task pool in OpenMP that contains all those tasks that have been created and are ready to be executed, then by the team of threads. So we still need a parallel region, at least in current versions of OpenMP, that execute those tasks. And having said that, the source code snippet on the upper right-hand corner of the slide shows how to parallelize such an unbounded while loop. As long as element is not a null pointer, a task is created that performs the compute on each element. It becomes obvious that this actual element, LM, this pointer has to be part of the task. So the environment has to be captured. That means the task is able to be executed correctly at whatever later point in time the runtime might decide to schedule it. So managing the data environment with tasking is similarly a challenge as managing the data environment with a parallel region. I said it already, a task can be created by a single thread. So we have a parallel master or parallel single pattern, which is often the case, but we can also create tasks from within a parallel region or from within a worksharing construct, and tasks can create even more tasks. And all threads in the team are candidates to execute tasks, and we do so by the latest at the next barrier that's being encountered, because the barrier can only be passed after all previously generated tasks have been completed. On this slide and the following slide, I would like to briefly present the constructs and then talk more about, I hope, interesting concepts. So pragma OMP task is a construct. It again consists of the so-called structured block and an optional set of clauses. So the structured block contains or denotes the code that's part of the task, and that obviously includes all the other code that's being called from within the structured block. So a task can be foo calls bar, and so forth, and bar is then obviously also part of a task. And here on this slide, we categorized the clauses in the, or we put the clauses that can be put on the task construct into different categories. So we have those data environment clauses, private, first private, make sure that you get a new instance of the given variable inside the task, with first private meaning the variable is initialized with a value at the time the task is being created. Shared means there's a pointer, and with default, you can override the default settings of the runtime. I will explain in reduction later on. We have some tunables like if, mergeable, and final. So if can override the setting of the runtime to decide if a task will be executed now or if it will be delayed. If evaluates to false, a task will be created but executed immediately. Mergeable means the data environment can be merged with the outer level or the enclosing construct. So that means private variables will not be created as new variables. And then final is an assertion to the runtime that no further tasks will be created. Mergeable and final are nice, but so far they are not implemented, and this is why in any product compiler, and this is why I don't have them in detail on the slides. We have synchronization clauses, dependencies, that will be a different chapter later on. I will also talk about scheduling, untitled, priority, and affinity. And again, on the MISC part, that is the reference to the memory management. This is something that I mostly will skip today, but with allocate, we can, for example, denote that the variable occurring here will be allocated in a different kind of memory, like the high bandwidth memory or the large capacity memory, whatever you might have in your machine. So most of those clauses, I guess, are familiar if you have used Openmp worksharing before, and all those task-specific things will be covered in the next, 30 minutes or 20 minutes. The other interesting construct is the so-called task loop construct. And with that, we can parallelize structured for loops. And maybe in the future, we can also parallelize while loops and so forth, but this is not done yet, or not possible in all situations. So a structured for loop is basically a for loop where the number of iterations can be counted. That means it's known before the loop is being, the execution of the iterations is being started. And that enables the runtime with the help of the compiler, which prepared the program to do so, to actually come up with different schemes to execute such a loop. Why do we need that? Well, there are some good use cases for a task loop, in particular when the loop iterations are of very different computational cost. So that means some take long, some take significantly shorter. With the for worksharing schedule, you can work with a dynamic schedule, but the for worksharing still, let's say, enforces a certain order within the chunks, which means that even with a dynamic schedule, the load balancing has certain limits, in particular when the costly iterations are being encountered toward the end of the for loop, just as a single example. In addition, worksharing has problems when you want to write parallelism or parallel programs on multiple levels because they are not composable. So with a task loop, you can specify either a grain size or the number of tasks. And the grain size means with a given value, this number of iterations are being put together to form an individual task, while numTask specifies an approximate number of tasks that shall be used when decomposing the for loop into tasks. And with that, I would like to highlight the difference. So the worksharing construct partitions a loop into blocks and executes those blocks on threads, while the task loop actually decomposes the loop into tasks. And then, unless there are special dependencies, priorities, and so forth, the task can be executed possibly in a different order than the loop iterations in the original corresponding for loop. And that can give you additional scalability advantages. However, if you do something like stream, don't get me wrong, the parallel for is still the much more efficient solution. So you need to select the right tool for your job at hand. Finally, let's look at the basics with respect to task synchronization, now that we can express tasks. The construct that was already shown on the slide before is the so-called task wait construct. And it waits, or the task wait directive, sorry. It waits for all direct children tasks, or direct, I tend to say child tasks, but I think it's direct children. but not all further descendants. And this is important for recursive algorithms. So we have an example here, and that's actually a slide from our tutorials. We have a parallel single, so that means a single thread is executing the body here, the structured block. We have a task that's called A. This task A creates two more tasks, which are called B and C. And let's further complicate it. C creates two more tasks named C1 and C2. And then we encounter the task wait here. So what will the task wait directive actually wait for? Well, it will wait only for B and C, but not for C1 and C2. That's what I meant with just the direct children, not any further descendants. And we need that in the recursive computation, for example, in Sudoku, but more obviously when you do a graph search, or even in a very simple case of a Fibonacci, you only want to wait for the direct children, take their result, and then resume, compute the result in the case of Fibonacci and so forth. So that means this task wait will wait for B and C, but not C1 and C2. And this is why task wait is the most common synchronization construct in recursive algorithms. I hope I made that clear with this brevity. If you need stronger synchronization, we have the so-called task group. And there are also other use cases for that in the context of reductions that I will show later on. And that will wait for all the tasks that are being created within this, within the dynamic extent of the task group. So here, now the code is slightly different. The block A does not consist of an individual task, but the task group. But then we have tasks B, C, C1, and C2. So the task group will wait for all the tasks that are being created within the dynamic extent, and only then the program will continue. So this is the two different kinds of task-specific synchronization, in addition to the dependencies that I will cover later on. How are tasks being executed? Again, let's take a closer look. So by default, tasks are being tied. That means if a certain thread, and with that here I'm trying, this is an initial thread, and then we have the single construct that might be executed, for example, by thread 1, with thread ID 1. Then the single creates the task foo, a task yield, and then bar. And that means foo, being part of the task, might be executed by thread 0 again. So thread 1 is creating the task, and thread 0 might pick it up from the task queue or task pool, depending on how you want to name it. With task yield, you can instruct the runtime to actually suspend the execution of the current task, do something different, and then come back. And there are some scenarios where you want to do that. For example, if you have some long-running tasks that might do some, let's say, expensive computations like I/O, or long-running computations like I/O, and they might be blocking other tasks to make progress, which might be important, for example, to generate additional tasks. It's a little bit complicated to think about that with actual code, but I didn't want to go into much detail here. But in summary, the task yield can improve the scheduling of tasks if you encounter situations where the task queue or the threads become underutilized because there are not enough tasks in your task queue. The other option is to use the untied clause, or it's not necessarily another option. The other option for tasks with respect to scheduling means it's the untied case. So if you add this clause to the task construct, then it's allowed for the runtime to suspend a task being executed, in this example by thread 0, and resume, here the bar, in this example with thread 2. So previously it was designed, or the untied feature was designed to enable the runtime to interrupt a task whenever it thinks it's suitable, but this is not allowed anymore. So only at so-called task scheduling points like child task, the task yield, and so forth, tasks can be interrupted, but and then in the case of untied tasks, be executed somewhere else. By default, the thread that picked up the task for execution will be responsible to completely to run it to the very end. And why did I include this slide here? So for many years in our tutorials, we said untied is nice in theory, but has no practical effect because compilers obviously can ignore it. now implementations are starting to make a difference. So that's good news. Yeah? So for some use cases, we see a performance improvement. And also another feature, for many years, we heard in our tutorials that tasking is nice, but it doesn't give us this and that. Yeah? The most important this and that was named were so-called reductions. Yeah? And people needed reductions in tasks to be able to utilize that feature. I can understand that. Yeah? There were workarounds before, but now this is possible. And actually, there are two ways to do that. So the first is to make use of a task group, register a variable, in this case res, to be part of the task reduction, and then within a task, say in reduction with a corresponding variable res and the corresponding reduction operation. So why is it necessary? Well, in a reduction, you need a well-defined point in the program at which the reduction will actually happen. Yeah, during the task parallel computation, or similarly to a thread parallel computation, the threads, and here the tasks are computing, I would call them partial results. And you need a well-defined point at which these or when you apply the minimum operation and so forth. So that means for your program logic at which to know when the reduction actually is completed. And for some releases of OpenMP where we're missing the task group construct, and also there's a challenge in to avoid race conditions and so forth. And this is why it took a while to actually include that feature into OpenMP. So option one is with a task group to register a variable with a task reduction and then use an in reduction clause on each task. And here at point 3, at the end of the task group, it's well defined that the reduction has been completed. The other is to perform it on the level of a parallel region. You have to add the special modifier, excuse me, to the reduction clause. And again, within the computation, use a task with an in reduction clause, and then the reduction will be completed at the end of the parallel region. This is a simpler case if you have, let's say, a single parallel region in which all the tasks are being created. And that means you don't need the task group construct. There's no performance advantage or disadvantage in using one or the other of these options. Again, we have to register a variable for a task reduction to make sure that the runtime allocates sufficient memory within each task. So again, this is a feature often requested by the community that's now part not only in the standard, but also in current implementations. Let's look at some more complicated features. So the first is task dependencies. Oh, also the animation is broken here, so let me complete the slide immediately. So OpenMP version 4, I believe in 2008, introduced the depend clause on the task construct. Then in version 4.5, it was added to the target constructs. And with that, I think OpenMP fully supported asynchronous GPU programming or asynchronous kernel offloading. And because target, meaning a kernel offload, is also a task, we can make use of task dependencies to express data flow dependencies between data management directives or the kernel offloads between the host and the device. OpenMP 4 made task dependencies more powerful. In fact, it included the most funny name in OpenMP or keyword, mutex in out set, and I have an illustration on that later on. And then in OpenMP version 5.1, recently released, I think it's a previous SC, we skipped the mutex as an additional option of an in-out set. So let me explain what that means. So a task cannot be executed until all its predecessor tasks are being completed. And here I'm talking about the semantics of the depend clause. And we can define dependencies over variables. The idea is that we have or that we organize the dependencies in terms of the data flow, so that you can hopefully make use of the variables that are already present in your program to express the dependencies. There are two different kinds of dependencies. There's the independency, and there's an out or in-out dependency. Two keywords with exactly the same semantics for whatever reason. So an independency will wait for all previously generated sibling tasks that reference the variable previously in an out or an in-out dependency. What does that mean? So the independence means the task consumes this variable, while an out dependence means the variable produces, the task produces a certain value into such a variable, or it provides a value into such a variable. And in-out means it both consumes and produces. And that means for that, if there's has been a task with an out dependence before that, it has to wait because it wants to consume that value. Before I add more words, let me show that with an example. So T1 here has an in-out dependency on the variable x, and x is a variable shared here in the region, so accessible by all the tasks. This provides this variable x. In-out means it both consumes it and writes to it. And T2 and T3 both consume x, but they do not modify x. That means they do not provide any value in there. And that means T2 and T3 can only be executed after T1 has been completed, but they can be completed simultaneously. And then finally, T4 has an in-out dependency, so it's consuming x, and again, it's providing a value in x, and that means because it's not only consuming but also modifying x, it can only be executed after both T2 and T3 have been completed. So think of the data flow, production or provisioning of values, and consumption of values, which can guide you in the expression of dependencies. Now, having a feature like that, there are so many special use cases, and there is always this one application programmer who needs additional functionality. And this is what Openmp in version 5 and 5.1 answered. So let's think of this example. So we have an output dependency on res, an out dependency on x, and an out dependency on y. And then now the Zoom window is in my way here. We have T0, T1, and T2. Sorry. Then we have an independency on x and an in-out dependency on res. So that means T3 has to wait for T1. I hope I explained it correctly because I don't see the right-hand side of the slide. And it also has to wait on T0 because it's consuming res. And the T0 is providing res. Then we have T4. So T4 again has to wait for T3 because of res, and it's consuming y. So that means it has to wait for T2 because T2 is providing a value in y. And then we have finally T5, which consumes res. So it's waiting for T4, if I see that correctly. Yes, that's the only dependency. So if everything goes according to the plan, you see the task graph here on the right-hand side. However, there might be applications where this is too strict. We need the dependency in between individual tasks, but it generates a chain of dependencies which is stricter than what our application actually requires. And this is why we can also specify the so-called mutex in-out set, which means mutual exclusion in-out set. Funny name. We had many other nice proposals on the table, but that one made it. So it means T3 and T2 can either be executed within this cloud of dependencies, depending on application, at the same time, or they have to wait until their dependencies are fulfilled, but then have to be executed, in the case of mutex in-out set, mutually exclusive. So that means we can relax this chain of dependencies, but still make sure that correctness is guaranteed, because then only one of the variables in this in-out set can be, one of the tasks in this in-out set can be executed at each point in time. That's the idea of the mutex in-out set. And with this support for dependencies, we have heard from many application programmers that all the features they are requesting are being implemented. But yeah, not all. So there's more on the next slide. So what we have added in addition is that you can also specify dependencies on a task wait. So that means it only waits for individual tasks. You can consider that syntactic sugar. However, we can also you can make good of use of that in the context of accelerator programming. For example, when you want to update data on the device asynchronous to making progress on both the host and the device, and then before you start the next kernel or launch the next kernel on the device, you have to wait for the update task to be completed. Then it's actually a good functional use and more than syntactic sugar. But I guess I don't have to go into much more detail here. So again, we have the data flow dependency. T1 produces X, and the task wait can only be passed after T1 has been completed. Because it consumes X. I think I explained that. So for those very few programmers, for example, writing linear algebra codes and so forth, or linear algebra libraries, that's actually what I wanted to say. Dependencies in the form that they can be specified here might not be enough, because in your program code, you either say in, out, or in, or out. And depending on some very clever optimizations, I can only understand when actually looking at the paper or the presentation. I couldn't reproduce it here. It might be important, or it might be necessary to actually change dependencies on the fly, or to be more precise, to be able to generate them programmatically. So this is what we can do with so-called dependency objects. I believe that's an OpenMP 5.1 feature. So the title of the talk, is not completely correct here, as I tried to say at the very beginning. So we can have variables of OMP depend t, declare them as a dependency object. So this is an instance of this variable, and specify the dependency type, and actually update the dependency type. And at the very end, we have to destroy them. So I have an example on that. And I hope you can see that. I can see at least part of that. So here we have a variable OB object or OBJ of this particular type. We declare to be a dependency object and specify the dependency. Then we have a task with a certain dependency. Here we have to specify not in, out, or whatever, but that's a dependency object. And here we can actually update the dependency. So we again reference this dependency object and say now this has to become an in dependence. And then we execute T2 only after the dependencies have been fulfilled. Here I have to admit that I don't have a very good example or a really important application use case proving that this feature has been successful in, for example, increasing parallelism, improving scalability, but I expect others have. So I'm looking forward to see examples of that in use in real application codes. Finally, we should clean up. Sorry, I forgot that. Now, coming towards the end, there are some clauses to optimize task scheduling. And many people have asked for that. Why can't I specify this particular thing I know about my algorithm so that the runtime can make very clever use out of that? And in many cases, the answer is because that would come with a significant overhead in the runtime. And that's what I would also like to emphasize in this subsection here. So what can be simply specified as a programmer cannot always be efficiently exploited by a runtime. That's my thesis here. So the first is a so-called priority clause. So assume that we have a team of threads that's available to execute tasks that are ready in the task pool. And I believe in this talk I didn't say it explicitly, but the Sudoku example I think gave you an expression. So if you have, let's say, 64 threads running on your system, you can have millions of tasks during the execution of your program. You can have probably hundreds of tasks at each point in time that are ready to be executed. So that means the task pool can be significantly larger, completely different orders of magnitudes than the thread team that's available. So if the threads have such a large pool to pick tasks from, we might influence this picking. And this is what the priority clause can provide. So if you have tasks with different priorities, all being available for execution or ready for execution, tasks with a higher priority will be scheduled earlier if the runtime follows your order. So the idea is whenever a thread is idle, it has to pick a task from the task pool, and then it can select the task with the highest priority. However, this is a hint. It's not a guarantee. So the runtime can ignore this clause, or it might have a good reason to actually do something different. And this is why you cannot make use of this priority clause to actually guarantee correctness. So this will not enforce the runtime to schedule those tasks with a higher priority earlier than the task with a lower priority. It's only a tunable. This is why I call them programmer's hints. Similarly, there's affinity. So for many years, we heard then in our tutorials after introducing support for NUMA and then introducing support for tasking, how do I combine this? There are good ways to do so, but for some applications, admittedly, as soon as you introduce tasking, affinity, data affinity on NUMA systems and so forth might become an issue. So this is why the affinity clause has been introduced. And the idea is that the runtime should execute tasks as closely as possible to the physical location of their data. And in practice, that means it should execute tasks by those threads that own the data or that are on the same NUMA node, for example, as the data. Again, this is a performance tunable. It doesn't have to do anything with correctness. So this is not dependencies. It has been shown in several applications to actually improve data locality, reduce memory, remote memory accesses, and in particular decrease runtime variability, because you can get in more iterations of the same executions of the same program, a more uniform behavior, because it becomes a little bit more reproducible. But if a thread is underutilized, even respecting the hint is not intended to forbid the runtime to steal tasks from a different thread. Idling threads is worse for performance in almost all cases than remote memory accesses. But why is this really a tricky thing? So let's assume for the runtime that a task region is encountered. So if it doesn't have a data affinity clause, then that's simple. It can push the task to, let's say, the local queue. In most implementations, each thread has a local task queue for performance reasons. And that is in many cases important, or let's say this question here is in many cases important for new features in OpenMP to be added, because a new feature that potentially is not used by many programs should not slow down almost all existing OpenMP programs. So that means if there's no clause on the task construct, no affinity clause, then no additional overhead is involved in executing through the task. Otherwise, such a feature would not find its way into OpenMP, is my personal opinion. If there is a clause, you have to understand, and that's why I'm in some more detail here, actually something pretty expensive happens. So the runtime has to understand where this data, the variable that's being referenced in the affinity clause, is actually located within the system. So that means you have to understand in which page this data is being allocated, and actually on which NUMA node, for example, the page is being located. That can be done pretty quickly for, let's say, the time feeling of a human being, but it takes quite a while for the time feeling of a modern processor. And this is why the runtimes usually implement something like a reference, a map of those references, so that if for a certain variable it has been figured out where it's located, this will be stored. And then the idea is to put the task into the queue of the other threads. So still stealing is avoided, but it's a better initial distribution. Otherwise, so if this map is not yet filled, the NUMA domain has to be identified then the right thread has to be located that actually is close to the NUMA domain. Possibly you have multiple threads there. You should select a good one and then update this map. So such a feature is certainly not just a hint that can be considered to be more or less free of overhead, just as a reminder. Good. With that, I'm coming to the end, hopefully still in time. Do you remember the motivation? Yeah, slightly different figure here. Sorry, that's a copy and paste mistake. I'm executing my Sudoku solver on this 32 threads, with this miserable speed up, to put it like that. So if we take a closer look, what happens? Well, we create millions of tasks. So this is a tool named Scalaska. Don't want to go into detail here, but these are individual threads. I think 8 of an individual program run, giving a statistic of how many OpenMP tasks have been created. And each thread here, 8 threads, is executing 1.3 million tasks in only 5.7 seconds. So that means, if I did the math right, and for many iterations of the slide, no one complained, the average duration of a task is in the order of 4 to 5 microseconds. That's really short. Taking a closer look, now this is screenshots with Vampire. In this recursion level on level 6, the duration of an individual task is 0.16 seconds. But remember, here it contains many further, many children tasks, going or making progress within the Sudoku board. And at level 82, the duration of a task, assuming that this measurement is still reasonable, is only 2.2 microseconds. So that means tasks are getting really, really small. And at some point, the overhead of a task is higher than its actual execution time. So what can we do? We can implement some tunables like this if, or mergeable and final. So in most cases, if, or we can implement it in our program to make sure that after we have created enough tasks, no further tasks are being executed. And with that, we get a speed up of close to 16 on a system with 16 physical cores. So I didn't go into algorithmic details here, but this, I call it the cutoff, or the literature called it the cutoff. So it means this decision factor at which time in the program enough parallelism has been expressed is a really important tunable in task parallel recursive algorithms. Which brings me to the final slide. What did I leave out? I didn't talk about cancellation. It's not only a task-related feature, but it's often used in tasking. So for example, if you search in a tree or in general in a graph, as soon as you have found a certain element, you want to cancel the parallel computation, and you can actually cancel at the granularity of a task group. Again, it's interesting if you have a task that's generating more tasks while another is trying to cancel everything. The runtime has a hard job. So in parallel programming, cancellation, except for program termination, can't be achieved immediately. So it's an as soon as possible coming to synchronization points. And also what I didn't cover is what I call the asynchronous API interaction, so that there are mechanisms to marry asynchronous APIs like CUDA, to some extent also MPI, with the model of OpenMP, because I can have an example on that in the next talk about offloading. That's it. Thank you very much.
Thanks a lot, Christian, for this very interesting and entertaining talk. First of all, are there any questions? Please use the raise hand feature so we can see when you have a question. Call your name. Josef.
Yeah, I have a question about the Affinity. So I think that's very interesting. I was just wondering, is there plans to have a way, I think, to speed this Affinity cache somehow? I can imagine that if I do an initialization, I could already fill up that cache for later Affinity clauses or tasks. Or is this always asking the operating system in the background, as far as I understand?
So this is asking the operating system. So there's There have been proposals like that, but I believe the standard implementation is pretty much what I've shown here. So there's a paper reference. My colleague Yannis has been involved there. Just to illustrate, there's much more details, for example, to find out where pages actually costs quite a bit on Linux. So there's no cleverness in standard OpenMP implementations.
Okay. And a similar thing was just a question. At some point in the past, there was something like migrate or next touch proposed by different people. So that could be probably also similar to Affinity, but more that data is migrated where the thread is about to be executed. But
Correct.
there's nothing on that, or?
Yeah, so we also proposed that together with others. But we also measured the cost. So migration, that means using an mmap or something like that to artificially trigger a page fault, figure out which page, migrate, and so forth is really expensive. So that was the main reason why this didn't find its way into OpenMP, because people would probably make use of that with a wrong expectation about performance. So it's really expensive. You don't want to have that every time. You could ask for something, let's say, every so and so many time steps. And with that, you have functionality like AutoNuma, I hope that's the right name in Linux, which can achieve similar things. It's not always suited for HPC applications, but it was determined that this is nothing that OpenMP at the moment should implement.
Okay.
But there are libraries which could give you something close to OpenMP functionality then with the cost that I just mentioned, so that you can equip your program with that functionality.
Okay, thanks.
You're welcome.
One comment about that, it's also our experience that at least in simple cases, you can let the Linux kernel figure it all out using the NUMA balancing feature. Yeah. And it's really reluctant, it's slow, but it has to be slow. If it's over aggressive, then it keeps moving around pages, which is not possible.
Yes. Yeah. Okay, AutoNuma is, I believe, what you reference as a NUMA balancer. Maybe that's an official name now.
I think it's called NUMA balancing, right?
Yeah.
Auto page migration.
Yes.
Any more questions? Because I have some. Okay, so yes, Chrissy?
I was wondering, for example, can you have, for example, within a multiple task pools, for example, and then you could give, for example, for each of the NUMA domains, different task pools, right? So, for example, it might help, for example, in case of applications like where you have load imbalance, for example, sparse matrix vector, for example. You could keep multiple task pools, and then you should also be able to assign only certain number of threads to this task pools. Can we do that?
Yes and no. So in OpenMP implementation, I believe it's done the other way around. So each thread, in, let's say, the reference implementation, the LLVM implementation that's also used by Intel, IBM, and so forth, each thread has a task pool. And I believe it is by default 256 tasks or something like that. The numbers might not be up to date. I looked at the implementation details 2 or 3 years ago. So it means each thread has a task pool. And here I try to illustrate that. And that means when a thread encounters a task construct, it puts the task into its local queue. This is not part of the OpenMP standard, but done part of an implementation detail. Whenever a thread encounters a synchronization construct like a barrier, it will look to have local task queue. If not, it will take a look, are there other tasks in the queue? If yes, are there tasks available in other queues? If yes, it will try to steal tasks. So it means it will randomly select a task queue and then take a task from there. And if there's nothing else, it will try to steal again, and will also keep a preference of a removed task queue if it was successful stealing there before. So minor details might change from version to version, but that's the idea. So at the moment, you cannot assign threads to a task pool, but you have technically a task pool. What I try to illustrate here, one per parallel team, but you have stealing. What is planned for OpenMP 6 are so-called task-only threads. There are also more funny names available for that, but I believe that's a current a working title. That means you can have a kind of invisible thread pool that's only available to execute tasks, which would give you an execution model that's very similar to Intel threading building block, for example. So, and with every thread having in a local task pool, you also have some NUMA optimization, because if you bind threads, you have the task pools per NUMA node, and then there's some priority in the stealing. But there are interesting papers, so trying to steal locally from a NUMA node first is not necessarily a good idea for most programs, because then you actually version load imbalances. So this is why randomized stealing for, let's say, a larger set of programs is a more, it's a better approach.
Okay, thank you. And one more question. So regarding performance, what would be your, so obviously tasking has some performance overhead, right? So what would be your suggestion on when to use tasking and when not to use tasking?
I mean, whenever you encounter, let's say, a performance limit with traditional work sharing, you should consider tasking. Whenever you have a recursive problem, an irregular problem, and so forth, you should consider tasking. When you have, let's say, an operation like a matrix vector multiplication, there's no reason to use tasking, because work sharing was made for that. You have perfectly foreseeable memory access. The compiler can do the best optimization. And I believe you mentioned sparse matrix vector multiplication beforehand. So for that, you might be successful with tasks, but I would believe that in most cases, if you can take a look at the structure of the matrix, you can actually compute the optimal schedule yourself. So we applied that to several codes, and in all codes, this was the best possible approach. So if you have that knowledge, you do not have to let the runtime figure that out, because a runtime can't do a better job than what you would do if you incorporate that knowledge a priori.
Yes, thanks a lot.
You're welcome.
I have a question about dependencies. In the standard, it says that if you formulate a dependency with a depend clause, then the item which it depends on is one of the list items in tasks that were previously spawned. So the problem is with this expression, one of the list items. A list item can also be a slice of an array, for example.
Yes.
How do runtimes handle that? Do they really actually compare array slices and whether they overlap?
Okay.
Or is it just
so
a
first,
starting
you
address?
always have to use the same slice. So if you have a slice A to N and you want to have a dependency of A1, this is not allowed.
Okay.
And this gives you a hint of what the runtime is doing. So it's looking at the base address and probably a length. So it's not comparing slices element by element.
All right. So that's what I suspected.
Yeah. So.
Right. Another question about task groups and reductions. So it's very interesting that we can have bags of tasks with reductions now, but as opposed to reductions in standard work shared loops, there's a problem here because potentially you generate many more copies of the reduction variable, because you can't just have one copy per thread as you have in a work shared loop. It's easy because you need one private copy per thread, and in the end you reduce them to one result. But if you have a lot of tasks with a lot of copies of the reduction variable, this can get also out of hand. These could be array slices as well. Is that a potential problem?
So the potential problem would be that you have too many private data per task, too much private data per task.
Let's say you have a lot of private data per task, or a lot of data in the reduction variable, like if it's an array, for example.
Yes.
And then you have a lot of tasks which are part of this reduction, probably in different parts of your program, which is the part of the same task group. So potentially there are many more copies of the reduction variable than there are threads.
Yes. So, I mean, potentially that could be a problem. However, I haven't seen that before. So the numbers would be, you have, let's say, 64 threads times 256 tasks. Yeah? If that times the size of the private variable is too much for your memory, for your system, then you encounter the problem that you just sketched, if I understood you correctly.
Yeah, exactly.
I believe in such a use case, you should think if that really has to be private variable, if you couldn't work with shared accesses and synchronization. The other opportunity would be to limit the number of tasks. Yeah? Like in this particular example, you could do more iterations of the while loop within each task, for example. But so tasks consume some memory, and that's why there's a certain limit of the number of, let's say, tasks that can be ready for execution. I'm not aware of any runtime that also takes a look at the memory consumption at the moment. So in theory, they could. So that means whenever a task is being encountered, the runtime could see, oh, am I in danger of running out of memory? Yeah, and if so, execute tasks immediately instead of creating new ones, but I'm not aware of any runtime doing that, and I'm not aware of a real use case. So if you have something like that, that would be interesting to look at. But I guess then you have to restructure your code.
Okay. Any more questions from the audience? I have a final one about task priorities.
Yes.
If you attach priorities to tasks, is it possible in certain situations to starve low priority tasks by continuously submitting higher priority tasks? Or do the runtimes account for that by having some kind of, automatically increasing priority in the background so that a task which has been waiting for a long time eventually will be executed, even though you're submitting a high priority task?
Okay. So it depends on the structure with which you're generating the task, I believe. Yeah, assuming that all those tasks become executable or ready for execution, then potentially low priority tasks might starve. Yeah. But this is an implementation detail. There's nothing in the OpenMP spec that's addressing this problem. But if you take a look at the algorithmic structure, I believe at some point, this will end. Yeah, you can't. Within the same for loop or a while loop, you can continuously generate tasks. Yeah?
They will be executed eventually.
You realize I'm still thinking about it. So I think if here this size is long enough, if you generate long tasks, it might become pretty boring for those low priority tasks. So it might wait for a certain while. But at some point, when your program completes, there's a synchronization construct, and then all tasks have to be completed before you can continue. Yeah. There's nothing within the runtime and nothing foreseen by the OpenMP standard that would take care of that, like whatever, an auto priority increase.
Okay. So in the end,
at least I'm not aware of that.
One could give the advice that if there's a potential of low priority tasks being starved, and that might be a problem for your code, then you shouldn't structure your program in that way. You should do it differently.
I agree. Yeah.
Okay. All right. So if there are no more questions from the audience, I think this is it. Thanks again, Christian, for this.
Thank you very much. My pleasure.
And goodbye, everyone, till the next NHR PerfLab seminar. Bye-bye.
Bye-bye.